Welcome to Drone Systems and Control course. This particular module is on dynamics models of multirotor. Okay. In the last lecture, we talked about rigid body transformations, and we talked about coordinate transformations, and we also discussed about inertial frame, body frame, how do you do the transformation from inertial frame, body frame, and what's Euler angles. All these will really help us to understand building the model, dynamic model of the multirotor system. This is very important because if you are trying to develop the control law, you need to verify in the model first and get a confidence, then we can look at the implementation. So dynamic model and control is a very important part, right? This particular lecture has three objectives. First, we start with multirotor dynamics fundamentals. We try to understand the relationship force, particularly thrust and drag, moments which is acting on the multirotor system. We derive the equations of motion based on the Euler, Newton-Euler dynamics. Then we look at the control input and output relationships. Here in multirotor, the input is the motor speed. How the motor speeds can be used to control the drone. What do we mean by controlling the drone? Moving the drone in a translational and rotational frame, right? X, Y, Z position and orientation, phi, theta, psi. How do we control that? Mapping we will understand. We look at explore the relationship between pitch, roll, yaw and altitude changes, how this going to happen, right? Once we did this, we look at how do we implement this dynamics in a way we can understand the performance or response of this multirotor system for various inputs. For this, we will look at MATLAB based implementation of dynamic models in simulation environment. This simulation environment will start adding sensor dynamics, will start adding the context in which the drone is going to fly, so that the response of the drone is as close as possible to the real environment. That is our objective. Once we do, we validate the response using experimental data. Hence, the future controller navigation module, whatever we are building, can be verified before deployed in the actual system, right? That is the objective. Just to give you a quick connection, we know multirotors. We have various type of multirotor systems. 4 rotors is called quadcopters, hexacopters, octocopters are available. They are widely used for various applications. Applications ranging from agriculture. In agriculture, you can look at the spraying or plant life cycle inspections, right? Building inspections, survey purposes, monitoring, right? All these are various applications. Why multirotors are quite often used for these use cases? Because of its mechanical simplicity, right? And now we will try to understand how the propulsion system is there, how we can mathematically model so that we can achieve the hover characteristics of the multirotor system, right? How the motor propeller combinations act and the actuator which is helping you to achieve this, how do we mathematically model it, how the dynamics can be made stable, and those are the things we will go to look at it, right? First, let us get into the basics of multirotor dynamics, right? First thing you need to understand, this is an underactuated system. What we meant underactuated system, it has a fewer independent control inputs than the total degree of freedom. The total degree of freedom what we have is 6, right? 3 for translation, that is x, y, z, and 3 for rotation, phi, theta, psi. So multirotor has a 6 degree of freedom, but we have only inputs, motors or speed is an input, right? We have 4 motors here, 4 motor speeds what we have as an input. These inputs independently will not control the translation or rotation. A combination of this will be useful for us to achieve the pitch, roll, yaw, right? The torque which is coming from the motor or the speed, thrust and speed which will be used to control the translation and rotation motions. They are not independent control of all 6 degree of freedom, hence they are underactuated system, right? For example, what I meant is if I want to get a forward motion, then I have to decrease the thrust T1, I have to increase the thrust T3, but total thrust should be good enough to managing the weight of the aircraft so that I can pitch forward. But when I am trying to do pitch forward, I will also have a orientation change will also take place. So it's not like an independent control that you can get. If you look at, if I change the torque, I can have a yaw motion, right? Yaw doesn't affect any other altitude or pitch or roll, right? So it's yaw you can achieve by controlling the total torque, but rest of the motions are not independently controlled. Again there your total thrust should be equal to weight. So that's the reason it is called underactuated system, right? So we know multirotors are underactuated. The dynamics is nonlinear in nature. You will understand in couple of minutes why I am talking of its nonlinear in nature. So we need to look at rigid body dynamics. We also understand the rotor dynamics. So that we can understand that how the thrust torques are generated using motor propulsion system. We have to derive the equation of motions for controlling and simulating the drone to get whatever the position and orientation we can get using the control input. So we need to understand the relationship between control input and the forces that I can produce, right. To derive the model, I have to make some assumptions. The first assumption is the whole aircraft, it's rigid body, right. Even though there is some amount of bending will take place, we just assume that it's very small and ignored. Second, we are assuming that they are symmetrical in nature, so that deriving a control input become easy. It's not necessary, but if it's necessary, it's easy to derive the equation of motion. The center of mass at the geometric center of the vehicle. The body fixed frame is at the UAV center. No aerodynamic drag for simplicity. When you are putting a payload, there will be a drag due to the flow, but we are assuming that is small and ignored. Okay, so that it is easy for us to derive the equation of motion. We have to have a reference frame. We will use an inertial frame, that is a world frame which is fixed for position and velocity, and we will have a body frame which is attached to the UAV, moves with the UAV, its body frame acts at the CG, that is an assumption, right. The transformation from inertial frame to body frame can be done using rotation matrix, which we covered in the previous lecture. So to simulate, we need to make some assumptions on state variable. Before I start looking at the mathematical model, I just have to give you some understanding. What is the objective of this modeling? We have a real multirotor system. I am giving some input to the real multirotor system, I get some response. What is my objective? I need to build a model. If I give the same input, the response from the model is also similar, right. I have to mimic the external environment, how it is going to affect the response. Those environment also have to be added, so that the response from the model, response from the real aircraft are as close as possible, so that we can validate our control, we can validate our navigation algorithms before we deploying it in actual field. For that we need to represent, we are going to use the following as a state variables: the position vector, which is in inertial frame x, y, z, orientation is Euler angles phi, theta, psi. We get a linear velocity in inertial frame, that is x dot, y dot, z dot, which is also called u, v and w. Then you have angular velocity in body frame, how the orientation changes, right, which is p, q, r, roll rate, pitch rate and yaw rate. And then you have a total thrust which is acting upwards. That thrust is generated by the rotors, right, and you have a gravity which is acting always downwards, and you have a moment which is due to different rotor speeds, right. Now before we go further, let us get a basic understanding of the propeller. We know there is a motor and the propeller is attached. The propeller has certain pitch characteristics, right, and I am just looking at a small section of the propeller, right, cross section, which is at a distance r from the axis of rotation, right, and that particular section, it is a typical aerofoil structure, right. I am assuming a free stream velocity which is represented by vector v, which is going like this, right, and the chord. This is angle of attack, this is psi, propeller pitch. What is a propeller pitch? What is the angle of attack, right? The theta, what we are talking of inflow angle, that is with respect to omega r. So, lift force of a section, which is represented by dl, which is acting, right, and I am resolving the lift force into two components. One is dt and other one is dh, right. This is the thrust component. What is dt? dt depends on how many propellers present in the system. Rho is the density, omega r, omega is the speed at which the motor spins, right, r is the radial distance. Then you have a coefficient of lift, which depends on Reynolds number and angle of attack, cr, this cross sectional area, and dr. I have to integrate this over the radius. If I integrate, I can get the thrust component. Similarly, the torque can be expressed as nb by 2 rho r omega r square. This depends on CD, Reynolds number, angle of attack, cr, dr, right. Now, this is derived based on blade element theory. I am not going into the details of the blade element theory. There is a reference material given at the end of the lecture. I request the students to go through this blade element theory to get a basic understanding of how to get the lift and drag component when we are trying to integrate over the rotational direction. Now, this relationship we have to approximate in numerical sense, or we have to approximate using experimental data. To get the relationship between the speed at which the motor rotates, that is a rotational speed omega or rpm, revolution per second, and the thrust component, we use what we call thrust bench. We connect the motor propeller and we connect the load cell, right. We instrument this to find out what is the thrust it is producing, what is the torque it is producing for a different rpm, and we record this information. Whatever blade element theory says, right, or whatever numerical calculation we can do for a specific propeller pitch, or we can use experimental setup to collect the relationship between the thrust and rpm, right. We measure at specific rpm and we try to quadratic fit to understand the relationship between thrust and rpm, similarly for torque and rpm, right. Now, we get into the quadcopter dynamics. For simplicity, the number of rotors I am assuming to be 4, so that we can derive, but same equations of motions are valid if you are going for multi-rotor system. You have two important dynamics, translational dynamics, rotational dynamics. The translational dynamics depends on the applied force, right. So, mv dot equal to mg, that is a force due to gravity, and then you have a body forces which is acting on the vehicle, right, multi-rotor system. R is a rotational matrix from body to inertial coordinate frame, because I am measuring all the velocity in inertial coordinate frame, right. Fb is a force acting on it. It is like x direction I am not applying any forces, y I am not applying any forces, z direction I have a thrust which is acting upwards, that is why it is minus t, right. You have a gravity vector is there, that is a mg component, right. The force for quadcopter, thrust per rotor, right, what is Ti? If I am trying to approximate that relationship, it is a quadratic, right. I can just say Ti is kf omega I square with respect to rpm. There is a constant with respect to that, the thrust can be measured, individual thrust. The drag per rotor, the torque that what we measured, it is also quadratic in nature. The tau di per rotor is some constant km omega I square. So, total thrust is T, that is summation of all Ti for quadcopter, T1 plus T2 plus T3 plus T4, but other multi-rotor system you should do sum of all, right. The torque depends on geometry and rotor layout, how the rotors are laid out. We will discuss this in later, right. If you look at the rotational dynamics, you have an inertia matrix comes into picture, IB into omega dot B plus omega B, it is into IB omega B, which is torque tau b. Tau b is the moment generated in the body frame. So, a typical single motor propeller system, I am just showing the thrust acting vertically upwards and there is a torque, right, that is tau d. Now, actuators are located, I am making a simple model, right. Actuators are located at the virtual square, right. So, you have the if you virtual square, if you are trying to connect all these, right, it becomes a square. Right. So, you can create it as a virtual square and you have motor propeller system is at every corner, right. Two opposite motors, these two are opposite motors, spin in the same direction clockwise, the other motors spins in anti-clockwise, counterclockwise direction, right. So, the differential thrust used to tilt and translate the vehicle in xy plane. Now, let us look at what is the condition to be in hover. Aircraft to stay still at a particular height h. What is the condition? T1 plus T2 plus T3 plus T4, the thrust produced by all four motors should be equal to mg, right. The gravitational force should be balanced by the thrust, right. And not just that, we also have to have T1 is equal to T2 equal to T3 and equal to T4. Now, I do not want any rotation in that particular plane, right. So, two rotors are rotating in clockwise, other two rotors are rotating in counterclockwise. So, tau d1 plus tau d3 is equal to tau d2 plus d4. So, when you have this, there is no rotation about z axis and the thrust is equal to weight. So, the aircraft start hovering at that particular point. Now, let us look at the translational equations of motion. Basically, I am trying to look at what is the velocity in inertial frame, right, rate of change of velocity m into ve. See here mass does not change. So, m can be taken out, it is equal to mg component plus the force comes into picture, right, force in inertial frame, right. So, I need to get that force vector in inertial frame, and if I want to represent that in a position I want to get it, right, x, y, z and double differentiating, right. Mg is equal to R into Fb, Fb is the force which is acting on the body frame. So, I have to do the translation and here the gravity I am just assuming 9.812 meter per second square, right. Now, comes to Euler angle, we are looking at rotation in z plane if you take psi and then rotation in x plane y plane if you take theta and psi, right. Phi theta psi is very important, which is required for us to represent the orientation of the vehicle, right. Euler angles are not globally defined, you need to understand, whereas the rotation matrix is globally and uniquely defined. One way to do is we can use quaternions, okay, and then we can do the transformations, so we can take care of it, right. So, if you look at the rigid body rotation equations, dou L E by dou T equal to dou I E omega E by dt, which is equal to tau E. When subscript E represents, it is an inertial frame, right. As quad moves in 3D space, moment of inertia and angular velocity vary in the inertial frame, which makes this solution complicated. Transforming the equation in the body frame of reference, so you can write it dou Lb by dt is omega b to Lb and tau b, right. So, if I am trying to do this Ib, which I talked about moment of inertia earlier, into d omega by dt, omega beta Ib omega b, which is tau b, right. At tau b, if I am trying to transform the inertial rotation to body frame, so I need to do the translation. See rotation matrix inverse, so that I can get the torque in the body frame. Omega b is P Q R, Ib, I am assuming symmetric. So, you have x, y and z will be there, right. If the symmetricity is not there, you will have the other component, off diagonal components will be there accordingly, okay. angular velocity of the quadcopter is not the time derivatives of the Euler angles. So, you have to understand that phi dot, psi dot, theta dot can be represented using the rotation matrix PQR, right. You can do the translation. Now, let us try to look at the control input. U, we have 4 inputs U1, U2, U3 and U4. I am not talking just the speed, right. I am trying to relate it in a way I can get the pitch motion, I can get the roll motion, I can get the yaw motion and I can get the height control. So, those are the input U1, U2, U3, U4. U1 is tau 4 minus tau 2, right. This T4 minus T2, this difference, right, and L is the length. U2 is T1 minus T3 times L. U3, right, this depends on torque, right. I am trying to get the yaw control, right, minus tau D1 plus tau D2 minus tau D3 plus tau D4. Remember, 2 rotors rotates in clockwise, 2 rotors rotate in counterclockwise, that is why my input comes, that will give the yaw control. Your U4 is the total thrust T1 plus T2 plus T3 plus T4. Okay. Now, if I am trying to write the 6 degree of freedom equation in general representation, m dou square p by dou t square equal to mg plus r into Fb. Fb is the force acting on the body frame. Simply translating, we can get x double dot, y double dot, z double dot, you get p dot, q dot, r dot, translational and rotation equation put together, that is your 6 degree of freedom motion, equation of motion, right. The control inputs, whatever we are doing, right, I wanted to connect U1, U2, U3, U4 to T1, T2, T3, T4, right. If I can do that, I can bring in the motor model which is RPM versus thrust control, right. How this thrust, if you look at U1, in the U1 is T4 minus T2, right. So, what I have done, right. So, I am trying to bring in T4 minus T2 times L, right. So, I try to rearrange with respect to T1, T2, T3, T4. This is control allocation matrix. If you look at the thrust produced by the motor is a constant K times omega square. The notion here I just put it capital omega because here I am talking about RPM. So, I introduce the capital omega. So, omega square, the torque is again proportional to constant and omega square. So, I put omega 1 square, omega 2 square, omega 3 square and omega 4 square. These are motor RPM. I am trying to transform that into the control allocation matrix. So, I just want to get the relation, I want a single constant. So, I introduce new constant called C. C is nothing but Q by K. So, this is my control allocation matrix which will give you U1, U2, U3, U4. It depends on motor speed. Now, motor is my actuator, right, which is helping the propeller to rotate at a specific RPM. So, we look at how the dynamics is going to play a role. The torque generated by motor tau m depends on a constant, motor constant I minus I naught, right. Therefore, its dynamics can be modified, right. So, J m, this is motor omega dot is kT into I minus I naught minus Q omega square, where I equal to, that is a current, V minus kV omega by R. So, I can get the motor constants and I can get the relationship. So, I have the actuator model also with us. What we need to know, what is the voltage, the battery, Jm is the moment of inertia of the motor, Kt is a motor torque constant, I naught is motor no load current, what is the current it is consuming when there is no load, right. R is a motor internal resistance, Kv is a motor back EMF. Once we have all the value, we can even model the motor dynamics, right. So, I will take you now through MATLAB demonstration how we can transform the equation of motions in MATLAB and simulate it. Okay. There is an MLX file will be uploaded in the folder which is for chapter 5 supplementary MLX file will help you, right. So, we are trying to represent the model in MATLAB. What is that we are trying to do? We are trying to give the state variable, we are trying to give the commands are my RPM, right. What is my RPM which goes into my motor, and I have to model the motor, I have to model the propeller velocities, right. Once we have, I can compute the torque and force that I can get, thrust force and torque that I can get from the motor propeller system, and that is passed on to airframe so that we can get the 6 degree of freedom model representation. The sensor block, I am just putting it hidden here. Once we cover the sensor lectures, I will show how these sensors can be modeled and how we can simulate the same, right. Now, we talked about propeller force generation. I talked about blade element theory. I do not want to go into details of the blade element theory. I showed you we can do an experimental setup to compute the thrust versus RPM, right. We can approximate it in a quadratic sense. We create the relationship between the power that what we are computing, and then we can bring in those equations, right. Now, before we go, we have to do configuration, right. What is the type of configuration we are looking at? The force which is thrust which is acting on is k time omega square. The torque which is acting on is again another constant time omega square. So, we get those informations directly, and we define the body coordinate system x, y and z, z is downward, right. Then we talk about UAV parameters, right. So, for example, we have to characterize how the mass is being distributed, right. When we derive the equation of motion, we made the assumption that it is a rigid body and it is constant, right. But if you look at the mass, there is a distribution of mass take place, right. If you take the X configuration of a quadcopter, there is a mass at the center which is basically your battery, your avionics, your sensors and your payload which is acting, that is the red dot representing one mass at the center. Then you have a motor propeller system, the electronic speed control will also be there. So, they are all lumped at the corner of the virtual square, right. There is one mass, 2, 3, 4. Motor 1 location we need with respect to center of mass, right. I am trying to put, if it is a square I am taking, I am looking at the each point how it is located with respect to center point CG, right. I am trying to represent the coordinates of these motors, right, assuming the center point where the CG is located is 0, 0, 0, right. So, I am trying to represent. Now, the sensors whatever I am doing, it may not be at the exactly at the center, right. We may putting the battery and everything slightly at a different height, whereas they are not displaced in XY plane. That is a coordinate where I am going to keep my sensors, I am representing at 0, 0, 0.8 H. So, this you need to measure, this information you need to add, right. Moment I do that, I have my x naught, I have my x1, x2, x3, x4. I have to mention what is my mass of the motor propeller plus EAC. I am just putting it here just for a reference here, right. I am putting all the masses, I can add all the information, then I can find out center of mass, right, and I can, that is my where the masses of all the 4 and this sensor masses being present, with that I can compute where the center of mass going to be and representing the center of mass as a 0, 0, 0. Okay. Then I have to find out what is the total mass, because I need the total mass for my equation of motion. That is what I am representing as a total mass. The mass is represented in kilogram here, right. I just took just the mass of the motor alone. I have taken the mass of my avionics. You can measure the actual mass and add these information in your equation of motion. So, it becomes easier, right. Once I have the total mass, the other important parameter that I need to get from the airframe point of view, that is my moment of inertia, right. For equation of motion derivation, we assume that it is symmetric, right. Otherwise, you will have x component, xy component, xz component, and similarly for yx, yz, zx, zy, and you will have a diagonal element ixx, iyy, izz, right. We need to compute all of this, right. So, to compute all these, we need to define where your mass and how the distribution is going to be there, so that we can compute. Either you can do your CAD design and bring those values, or you need to define where is your x naught, where is your dm naught, dm1, dm2, dm3 and dm4. dm1 to dm4 is your motor masses, right. dm naught is a lump mass I am assuming at, which is the sensors and battery which is located, right. But if you have a CAD model, you can compute your structural weight. You may have a landing gear distribution. With that you can compute your ixx, iyy, izz, and if there is any cross moment of inertia, you will be able to find out. Okay. Otherwise you can just provide them like this, automatically these equations will take it up. You can use the solid models, that is what I mentioned, right, and you can compute and implement directly also. Now, propeller system, how is the torque generated? That is what we discussed in our previous equation. We need to model the motors. Your motor constants are there, that you can bring it in and you can represent them in motor also. In summary, what will happen? You have total applied force, that is a thrust which is acting on all 4 motors, and you have a torque which is acting on all 4 motors. Remember, 2 motors runs in clockwise, other 2 motors runs in counterclockwise. So, you understand all of this, but that is not sufficient. We need to set up the practical limits. Hope it is very clear there. We need to set up the practical limits for these thrust forces, right, maximum forces that you can get, right. What I am really looking at, whatever the thrust generated by all 4 motors should be equal to mg. If maximum RPM I am running, right, at that this thrust is equal to mg, then it is very difficult for us to do maneuver. So, what we do, right, we just take twice the total weight. So, 50% throttle, I should be able to get the thrust forces which is equal to the gravity force. Okay. So, that you have remaining 50% for operation of your vehicle. So, to move them at a specific speed and all this, so you need to do that, right. So, that is why we take that into account. So, we need to limit this force generated, right, that limit we need. So, we have to do that limit include inside how my thrust, what is the minimum value, what is the maximum value I can get, I have to limit them so that I can simulate it accurately, right. How do we mix motor mix, that is control allocation matrix I talked about. We need to look at the rotation x, y, z and pitch. In our calculation I assume that there is no positional variation in all 4, they are perfectly symmetrical, but you may not be. So, you may have certain angles, you have to use those angles to compute your mixing matrix. So, you can just define what is a pitch phi theta psi, you can vary this. If you vary this accordingly, you can get your rotation matrix. Okay. So, I can control all these information to get down my rotation matrix. I already discussed how to get pitch, roll, yaw and thrust. So, we use that we can get the control matrix, mixing matrix. Okay. This is how we get the mixing matrix. The one difference in equation of motion when we did, we look at the thrust at U4 is at the bottom. When we are implementing here, U4 is at the top. So, thrust, then you have roll, pitch and yaw. Okay. So, I get the necessary matrix, I can add all these. So, I can get the function which is called rotate. So, you can rotate based on phi theta psi, you can get your rotation accurately, right. So, once we do this, we can simulate the whole system of equation. Just give me a minute, I will show you. I can get the representation. Okay. If you see here the block which I am pointing out by mouse, right, this is your body angle, Euler angle computation. Once I get my force and torque, I can compute the position, the states of the system, right, x, y, z, x dot, y dot, z dot, it is your velocity informations, then you can get phi theta psi, and you can get rotation values PQR. All these are your state which you can compute, right, and you can show whatever the state you wanted to see, right. And what is the input? You can provide what is the speed of your motor going to be, and you can provide that input, or you can whatever the realistic input you are given, you can pass on. This is your motor propeller model, right, based on your input, right, RPM, what should be the torque and force generated by the propellers. It's simulated in this, that is what we call UAV dynamics front end. I can generate, moment I get the force and torque, pass on to my Euler angles. I can simulate very easily for any specific forces and see the response, right. I am trying to give you how much distance x I am moving, y, x, y, x is the red, y is the blue, z is constant. Here I am trying to give you the motion. You see the response, there is some response is oscillating. You have to understand we are doing it without any control at this point of time, right. Open loop simulation is what we are doing. You can see an oscillation comes into picture in your roll, and whereas your pitch and yaw is almost 0, right. There is a huge roll is there. We will discuss about it. I am just given the input so that the uncontrolled response is what we are observing, right. So, I can emulate the 6 degree of freedom model in MATLAB. Okay. So, I can get all the data, and now what I can do, I can look at the CAD model, I can compute the Ix, Iy, Ix, including the structure mass distributions. You can just add those information. You can look at the landing gear, their position, their mass you can add, compute Ix, Iy, Z, substitute it here. You can do the bench test to get thrust benches. You can try to get the single motor propeller system, the relationship between RPM and then torque, you can update it. The particular motor constants if you have, you can just update it so that you can emulate this response. In the subsequent lecture, we will talk about sensors. There are important sensors. There are sensors which are required for control and navigation, the IMU inertial measurement unit. You may need a height sensor, which could be your single point LiDAR, or you can use a radar sensor, or you can use pitot tube. You can measure the height. You can measure IMU, which will give you your orientation and acceleration. So, you will have a 6 axis or 9 axis. 9 axis means it will have a magnetometer also, right. That is an internal sensor which I need. These sensors required for controlling the aircraft. Then you have external sensors, right. You can have a camera, it could be a monocular camera, or you can have a binocular camera which can get the depth, or you can have a LiDAR, you can have a radar which observe the environment in which the drone is moving. For example, if you wanted to avoid collision with respect to some other static object or moving object, we need these external sensors. In addition, we can also measure the wind disturbances, so the control become much more realistic. We will talk about those internal sensors, external sensors, how these can be where do we place them, that is another important aspect, right. Where do we place them, how fast they have to sample it, and once we discuss, we will also model them in MATLAB. Instead of just displaying it as an XYZ, we will bring in the sensor model. We will also bring in the scenario model where this drone is going to fly, where external sensor being present, and we replicate that. Once we complete this loop, right, it will be really useful for us to get into the control. We can try to understand if you give the external actual experimental input, we see the response in the actual drone, we can emulate the same thing in simulation environment, right. That is very important. Remember, not all states are measurable. If I use an IMU, I get acceleration, I get my rate, I may not get my attitude. I have to do estimation. We will talk about estimation. Once we have all these information and we look at the simulation again with sensor, with scenario and estimation. That completes understanding of modeling of the drone. Once we model, we look at the control and navigation in subsequent lecture. Thank you so much.